All right. Good morning. How are you? Can you hear me?
Good morning, Professor.
Good morning. Thank you for telling me. Okay. So we are going to start today. And what I would like to do is, first of all, to ask if you have any questions um, from what I described last time. And also, what I would like to remind you is I'm going to be sending a number of announcements throughout the course. So what you may want to do is to uh, there is a place where you can indicate that you want your um, to get notifications for your emails. And so I would suggest that you indicate that, because it's going to make it easier for you to know if, for example, I need to tell you something a few hours before the class for some reason, then you turn on the notification so you can see my emails. And I forgot to tell you. But other than this, so we'll start today. And um, what I will do is, for us to be able, I will keep this for my voice and for me to see you, but I will use an iPad that I have practically to be able to use Howdy and the material. And if I need to write something, it's easier for me to do that on iPad. So I will take control over the screen because I've been already class. Okay, so you will see how I'm going to do this. Let's see. Where did I? Oh, all right, so let me see here. I may have not done that, but I need to go to Zoom here, and I need to connect, start, open, join meeting. Okay, we'll do that, and I will stop the video from here. So I will have the opportunity to capture the screen whenever I want, and in fact, I will do it from here, so you can see how we plan to do this. So share screen here, start broadcast, and this is what you're gonna see, and then we'll go to. Okay, so here we go. Let me see. I have so many of those there. To get Canvas, we go to our class, and here we go. All right. So that's how you're going to be reading your home screen. And everything that I have, it's already incorporated here in this on this page. So for example, if we want to start talking about the four forces of nature, then I can increase that so for you, and then we can go and start looking at we'll start with this PowerPoint that I put together, because obviously the discussion about the forces that we observe in nature is not going to involve a lot of equations. We'll start just with understanding the physics. And then the equations will start on Monday about vectors. And then all of next week is going to be a review on vectors, coordinate systems, and a little bit of vector calculus, things that you have already seen, nothing new, but we're going to review them. Now, the one thing we're going to do today, and I will need to pay attention to time, is when in about 35 minutes, I will get on top hat, and then I will show you the quiz that I've discussed, which we are not going to take today, now in class, but I would like you to take it yourselves sometime between today and Monday, and just to practice a little bit and to feel comfortable. And I will, when we get there, I will explain. And I will explain also the type of problem that I gave you, which is kind of a review, and it's kind of fun, but you're going to get 60 points for doing it, not for accuracy at this point. So in any case, that's what we have to do today. So let's start with the fundamental forces of nature. Before I go there, is there anyone who can tell me how many forces we have been able to identify in nature? Who can tell me?
Four.
Four, exactly. And so I'm going here and I explain what those forces are. So first of all, which two forces, if you remember, historically, people were able to identify and conceptualize, not only feel it without knowing what it is, but to identify and conceptualize. Which two were those? I mean, like say 2,000 years ago, like 3,000 years ago, something like, no, 2,500 years ago, not 3,000. I don't think people had that capability. Tell me. So who can tell me? Yes. So from Lauren and from Miriam, they say gravity and electromagnetism. Yes. So practically was gravity, first of all, because they noticed when they took a stone, first of all, it was heavy, but then when they noticed that always things will go from higher altitude to lower altitude, always the same direction. So they identified that there was some kind of a force that kept us on the surface or on the lowest possible level that we could be. So that was gravity. They did not necessarily express it that way, but they were able to identify it. And then second was in electromagnetism, but in the following way. They noticed that specific stones, or like glass of some sort, kind of stones, when you would shine the surface, as they were trying to make jewelry for many years, they noticed that I was trying to shine the surface, clean it, and so forth. Then they could attract small pieces that did not have a lot of weight. And that became interesting to them, and they identified that there is a capability in some materials when you rub them on the surface to be able to attract for some time other materials. So these are the two, and then people start thinking about them. There was, of course, using narration rather than any other way. There was no way of expressing mathematically what happened. So gravity and electromagnetism. And then in the 19th and 20th century, people started thinking about these other two forces, which are nuclear in nature. So you see them in very small particles. And that's the weak nuclear force and the strong nuclear force. And that happened very recently. So another question that I have for you. When do you think we had the mathematics available that you see in a book of, like in the form that you see them today, in a book of electromagnetics? How soon do you think, or how far back do you think we started with this mathematical formulation? Can you say how many years? 200 years. You are absolutely correct. 200 years. So if you take the original book, not the original print, that probably nobody can afford it. But if you take the original book of Maxwell, what are you going to find? Which I found as a graduate student because I looked for it. I wanted to see how Maxwell wrote about electromagnetism. What did I find, you think? I found that he wrote essays to describe it. We did not have the vector calculus that we are going to learn now, or we are going to use in this class to be able to explain how electric and magnetic fields. So Maxwell wrote lines and lines to express Maxwell's equations, which in fact you can see how brilliant somebody should be, not to be able to think it conceptually, but even write it accurately using narration. All right. So that is the amazing thing. So all of these are important to understand how math has made it so easy for us right now to be able to write those things fast and understand what we mean. Okay. Here it says something extremely interesting, that the force that has been the longest known to us is the most challenging to explain. We still do not know very much about gravity. So Newton's equation that we still use, which is a macroscopic description of gravity, all right, is the only one we have. And only very recently, people were able to identify what they call gravitational waves, gravitational waves. And if you want to know more about gravity and the gravitational waves, you really need to look at some new experiments that they are doing, which are very deep inside the Earth. And they measure, in fact, the speed of some particles. But it has to be very deep, so they are not impacted by environmental factors. All right, so they're very far away from the surface. But in any case, interesting. However, this force that we identified first, and we still do not understand very well, is among the primary forces that is determining how space is developed. Now, of course, with electromagnetism, which was also a force that was identified, as we said, among the first ones. There was very recently the general theory of relativity, where it's very interesting because there is on the basis of mass and how gravity impacts the phenomena of the electric and magnetic phenomena in a mass. Then you have the bending of space and time, and together, especially because of gravity. So one of the most interesting phenomena in space that has also received major recognitions, especially recently with the Nobel Prize for the person who discovered the black holes, is a black hole. Okay, so now I would like to ask, does anybody know what is, or can anybody, first of all, know what a black hole is, and then try to explain what a black hole does? What is the function of a black hole? Who will be able? to tell me?
After the event horizon, a black hole bends space-time so much that all geodesics point towards the singularity.
Right. So what happens is the following. Not that we know very much, but we know enough and we have observed them. That is the interesting thing now. And that's why people now, eventually the theory was, so a black hole is a singularity in mass. What that means that in considering our space and how small we are in in the big space, all right, we're like a teeny particle inside the human body, if you think of even the Earth or our solar system. However, when you have extremely high density, and in fact, the distribution of mass density becomes like a singular function, like it has, it's like the unit function, all right? So the delta function, as we call it, zero everywhere almost, and then all of a sudden becomes like almost infinite. There, what happens is as other masses or other stars go close, then the gravity, and they move around it with a speed, then the gravity attracts them. And if I were to write here, let me show you where. So if this is a black hole, all right, and this is a mass that is coming, then like a planet, like a whole system, solar system. So this, how is it gonna go? It's gonna go like that. All right, do you agree with this? More or less it's gonna start going on this helix, and then going towards the end, and then it's absorbed. And then, so the black hole looks like this in space. I don't know whether I have here a picture of the black hole. I don't have it here, I don't believe. But the black hole looks like this. It's like a dark place because we cannot see it. And then around it, there are all kinds of, it's a cloud, because there are a lot of planets that eventually go towards the death. A lot of them. It's like a cloud here around the black hole. Okay, how does, so this is how it looks from 2 dimensions. How does a black hole look in 3D? Have you seen a picture of it? Does anybody know? Okay, so you know how it looks, and I will try to bring some pictures. I will try 3D. So consider this 2D here to be like this on one plane. All right, so this is one plane. And then, so all of the masses come here like this, and they go in, they are absorbed. And what comes out from here? Like one laser, what comes out from the other side?
High frequency electromagnetic radiation.
Energy of all types. Yes, so in reality, it's energy in the form of radiation. All right, so it's like so the black hole in this direction, if this is Z, it looks like something like that. If you like, all of this energy comes here in mass, excuse me, all of this mass comes here, and there is only energy going out here. So it's mass, energy. So what is it, a black hole for the universe? It's a transducer. Transducer. From what? From mass to energy. Very interesting, isn't it? It's a simple, giant transducer that takes mass on one end and then creates pure energy on the other. So interesting, all right? A lot of things come into play. So on one end, you have gravity. It takes everything in. Then you have nuclear forces and other forces, because people do believe that we don't know all of the forces in the universe because we cannot observe them. But there are a lot of other forces in addition to strong nuclear and all other kinds of forces that apply on the small particles. And eventually, all of the mass disappears and translates into energy. So there are pure transducers, a transformer, if you like, from mass to energy. Now, recently, to close the loop, all right, because this only gives us one transformer from mass to energy. So in fact, people will say, okay, then in reality, I can see the end of the universe, because if all mass goes into energy, then what is it? But now people have identified, both theoretically and now believe through observations, that there are other transformers, which we do not know yet, which change energy into mass. And it's not like an immediate transformation from all energy to all mass, but it's a point in time when energy from 100% energy, we start moving into energy plus mass. And they believe the Big Bang was one, at least, period where we started seeing that conversion from energy to mass. So that is the interesting thing in the universe. If you think in simple terms, it brings very complex topics into things that we can manage, at least to think about it. So the weak force. This is called weak because in reality, it's not that weak, as a matter of fact. It's a very important force, but happens in very small dimensions. And because it happens among very small particles and very small dimensions, in the scale of things, is considered to be small, and it's a nuclear interaction, and is mostly responsible for particle decay. So practically what happens, why do we say particle decay? When you hear particle decay, since we never so far have demonstrated that we have violated the second law of thermodynamics, since the sum between mass or the total energy has to remain the same, whether it is in the form of mass, has already transformed into mass, or whether it's pure energy. That implies that when a particle totally decays, there is energy that is generated. And this energy, a lot of times we observe because there are frequencies in every type of this transformation from mass to energy. There are frequencies that they are radiated and we see them. So another thing that I would like to have you at some point read, this is not for us the time to do it, is to talk about bosons, to read about bosons, which are some new particles that people say they carry force. Why is this important? A lot of the students will, and faculty too, in the early stages of their careers, will wonder why, let me be here, why an electric field on an electromagnetic field propagates even where there is absence of particles. All right, how is it possible, therefore, to have a propagation of the electromagnetic field at a time, in a place where there are no carriers, mass carriers, all right? No charges anywhere. Why? How can we see an electromagnetic field propagating without the presence of charges? That's an interesting question, isn't it? And it was a big question, and people were trying to speculate until people were able to measure particles which are called bosons. And these particles is very interesting. They can be only energy or they can be only mass. There are particles that in their life, they go from one to another. They call them force-carrying particles because they don't carry charges. They only carry some kind of a force. And since we are not exactly understanding what that means, we just define it like that. There are particles, they have no mass, but they carry a force. So I can be in a total ideal vacuum and I can still feel the force, the electromagnetic force in our case, that is of interest. And people believe that is happening with bosons. And of course, it's the strong nuclear force, which we know very well what it is. The strong nuclear force is responsible for, it releases so much energy that it makes it practically very useful or very dangerous. So that's how much I want to say at this point. Now, electromagnetic force. The electromagnetic force, and can somebody, in fact, define what is the electromagnetic force? Can you, if you were to define, in fact, it says here, it's called even the Lorentz force because he was the first one to define it. So what is this force? It's like a force if like trying to personalize charges. If one of us was a positive charge and the other negative or even positive, two charges in some proximity, appropriate proximity, will feel a similar, they will have, if we were charges. I'm personalizing, I'm not supposed to do that, but I do. And where in some proximity, we will feel on us a sense similar to what we feel with gravity. So if there were, you could think if charges were to have senses and a brain, and a negative and a positive charge were together, they would feel the same attraction like gravity, exactly the same feeling we would have. And if they were of opposite polarity, they would feel a repulsive force. So this is the beginning of how electromagnetics were developed. I have a question for you now. Why do you think Earth has a magnetic field? I have some pictures here to help you maybe. But what do you think? Why do you think Earth has a magnetic field?
Its iron core.
Yes. And what happens when you have an iron core?
It's ferromagnetic.
What happens is like you have small dipoles, all right? And we'll see that a little bit. It's like you have all of these small currents that go around, but because also there is a movement in the core. Do you agree with that?
Yes.
What happens? So all of these are moving in one direction or some specific directions. And if you have current that is moving, what is it doing?
Generating a magnetic field.
Yes. And is it good that we have a magnetic field or not? What do you think?
Good.
Why?
Because it protects from the sun's radiation.
Yes, it protects not only from the sun radiation, but from every, you know how many particles there are in the universe? Who know, those we know are many, and who knows how many we do not know yet. And particles are so small that they go through, I mean, if we were in a storm of particles, they would go through all of us. And what do we do when particles go through? Why is it bad for us to be in a storm of particles? Why do you think? What will particles do to our molecules and to our atoms? What does a particle do to an atom? A particle is a teeny bitty.
They corrupt and like decay them because like this is kind of the same with like radiation, isn't it? Like nuclear radiation causes cancer by denaturing
Yes,
enzymes and
yes,
body cells.
exactly. So think of this in a smaller size, all right? Because cells are big, in a smaller size. So you have the atom. The atom, what is the atom? It has a nucleus of particles and protons and neutrons there, all of them together with what kind of forces?
Nuclear forces.
Yes, thank you. Nuclear forces for the particle. They all have the same sign, as a matter of the same charges. There is not electromagnetic force because otherwise they will all go away, but they're held together because they're so much closer and nuclear is much stronger, hold together. And then you have the electrons around that they go. What kind of force is between the electrons and the nucleus?
Electromagnetic.
Yes, thank you. So now you have a teeny particle that comes with a lot of force, a lot of speed rather, and force also, I mean, when it hits. So what happens when this particle hits the nucleus?
It can break the nucleus.
Yes, it breaks it. And it breaks it, of course, when you break an atom, that's the end of it in its previous form. And if you start breaking atoms in a human body, then you have a total deterioration of all of the functions. And it goes like catastrophically, it goes like an avalanche. So, I mean, Earth would not be habitable if we did not have the magnetic field. Other than Earth, what do you think about our solar system? Does the solar system have a magnetic field?
The heliosphere.
Yes, thank you. So and it's not exactly, but here you see the magnetic field of the Earth and how it protects us and all of the life species on Earth from radiation from the sun, which in fact radiation comes with a lot of particles. All right, when we say solar radiation, we just don't mean heat. We mean a lot of both heat, particles, and a lot of energy rather in other forms. So electromagnetic force, therefore, in this particular case, it helps us as a planet, it helps our solar system as a system. And that's why Earth has been habitable, and then we're able to create life. Okay, any questions so far before I go a little further? Okay, the last thing I'm gonna say is the following. Why do you think I started with the concept of force and I did not go to fields directly?
Because a field is a bunch of different forces in different directions. Therefore, in order to understand what a field truly is, you need to understand what the different kinds of forces there are.
I mean, yes, you are saying it right. I will just say exactly you said in a slightly different way. I will say for us, species with senses and limited by our own sensors rather, and our ability to understand, we do not feel a field. We would not even know if there is a field that exists without anything that we can sense, all right? So we sense forces and without any other advanced sensors. We sense forces. And when you sense a force, the force that you sense depends on how you stand, where you are, your own physique, obviously. But if let's assume that your physique does not impact that for a moment, but your position, it's important in the kind of force you are feeling. All right, your movement at the time is important. So let's assume that I was like an observer, and I would go and sit in different places, from the top of a mountain to the lowest point of a valley. And I could somehow measure the force that I'm feeling. I would find different values. Is that right? Obviously. All right, let's assume about gravity. Assume that I had something could measure gravity easily, as a scalar rather. And then I would find different values. This set of data that I have measured, we call them a field. So the field is a region, is a mathematical thing. Okay, field is not a physical entity like we think of a force. The force is a physical entity, it exists. The field is not a physical entity, is a mathematical entity. We created the notion of the field to be able to describe the impact of forces, all right, of the various forces. So the electric field is really describing, it's a mathematical entity that describes a region that is affected by electric force. And also, when we talk about an electric field and we give equations, those equations describe exactly at each point how much in a given situation the electric force is. All right. Now, what is another thing in the field? That we have removed the impact of the observer. So you remember what I said, that it depends on my own physique. If I start measuring gravity, I will measure, say, if there are two people, one is a young kid, like 4 feet, and the other is a basketball player, like 7 feet something, and they have difference, of course, in weight and mass. When they start, if they were to measure the force that each one of them feels, they will find different values. Do you agree? Because it's the mass, all right? The mass of each other. It's different. Now, when therefore we want you and I that have we're different observers and have different physique, we wanted to measure the same the gravity force, and then start talking to each other and understanding what we are saying, we have to remove our own physique from the picture. How do we do that in force? By normalizing the forces with our own mass. So we remove, we'll see that in fact, if you go to the next one, then let me go back to home. And then if you go here to the next document, fields and forces, that's a document that is a Word file. You will see I'm talking about the fields there. I'm talking about forces. Now we come to this one. Look at this. This is the force. This is the Newton's force. And this one shows that they're the masses of the two bodies that are attracted in this particular case. If I am one of these, M1, for example, and M2 is another body, and the two of us have different M1 masses, but we are observing the M2 body, the same body. When we start talking about our observations, we have to remove what impacts our own observation, which is our own mass. So if I was a 4 feet observer and the other was a 7-foot observer with different masses, our masses have to come out. So when we go to the magnetic field, and I don't think I have it here, we are going to, gravity field, we are going to divide the gravity force by the mass of the observer. And as a matter of fact, I even have it here. If the observer is M2, then the gravity field is then only a function of the mass of the source divided by the distance between the observer and the source. And that is a field. It's a mathematical thing. Fields do not exist. We make them up to be able to understand with each other. Forces exist, all right? So with that, I would like to take us from forces to fields, so we are able to understand physically why we work with fields all the time and what fields mean. So in this class, not only we're going to see math, but we're going to try to understand what this math tells us and why we do it, okay? Right, with that, any questions so far in the material we covered today?
What's that blue line on the picture? R12. What does this stand for again?
This is a vector. When you see a little hat like this, we'll talk about that in next week. The little hat shows a unit vector. And a unit vector has the magnitude of 1, and the direction in this particular case shows the direction of the force. We're gonna introduce all of these concepts on Monday.
Okay, thank you.
You're welcome. Any other questions? Okay, now let's try to, I will show you the problem that you have to take. And since it's gonna only be, if you take it, all of the 60 points, then it does not matter, but you're gonna try to test it, take it on your own time. It's gonna be for 5 minutes. So I believe I have set it for 300 seconds. And I'm gonna make sure that when you see when you get to try to take the problem, try to finish it in 5 minutes, I would say 300 seconds, 5 minutes. Try to finish it then, just to also test that it works like that. And then I will go and show to you what kind of problem it is and how you're gonna solve these problems. So that's gonna be on your own time between now and Monday. Test it to make sure that you have access to it, and send me if you have any problems, let me know. Send me any questions you may have over the weekend, all right? Because Monday we're gonna have an exercise. Every Friday we're gonna have a quiz. Any questions before I go there?
Professor, you said the quiz is going to be on Top Hat, correct?
Yes.
Okay.
I don't know why that came up, so. All right, let's go.
Is it currently available on Top Hat right now or not really?
I will make it available now. I have to turn it on. Okay. So well, the only thing I have not tested, here. The only thing I have not tested, and I would like, at this moment, I may change that. I would like to test it. Let me, okay. Okay, you see how, do you see what I see here when you get into Top Hat? Could you try to get into Top Hat and tell me what you see?
It's just blank for me.
But on the left hand, do you see anything?
No, I don't see anything at all. Just classroom, assigned, gradebook, and they're each empty.
So the
That's
content, when you go to content, is it all empty, nothing else? Okay,
I don't have content.
You don't have it. Let me assign it. When I assign something, what do you see?
It just popped up.
Yeah,
Okay.
something just popped up.
Okay, then I will make everything for a review so you will see one of the other. Do you see what came up?
Mm-hmm.
Okay. Now, this one, can I do the following? Can one of you, I gave you access to, could you show us what you see so I can see what you see? Could you share? One of you. So I'm gonna see what you see because I don't have that capability. Okay, Nikolai will do that. But I don't see, do you see his share? I need to undo my share. Just a second. Stop. Okay. That's what you see, Nikolai. Perfect. Okay, so now let's talk about this. In this one, on the left, here is an interesting problem. I want you to think about this. You see it now, think about it before you take the exam. It's also gonna be a nice thing to review. It has two vectors. The vertical line shows magnitude, all right? We're gonna see all of this. I just gave it to you just for fun, since it's all on axis. I mean, you don't have to answer. You don't get graded for answer here. It says, worth 60 participant points. You see in the tab, does it say that to you? If it does not say, I'll tell you that. Yes, it does not say it, but it is 60 participation points and 0 correctness points. Participation is more important in this one to test it. Okay, what it shows here, you have to match and then you can move those answers. So say, if one, meaning the magnitude of vector A plus vector B is less than the magnitude of vector A minus vector B, then you will have to find the right answer. So you have to move. If you think C is correct, you will have to move it up. It is movable. If you think that something else is correct, you will have to move it around, play a little bit. And then, so the angle theta in one of these three cases is 90. In one of these cases is less than 90. In one of these cases is higher than 90. All right. So this is more or less how I'm going to give you some of the problems. Of course, they're going to be related to the lecture. This is like we have not done the review. So, but this is something you may have seen in the past. But of course, every day is going to be one problem like this. It's going to be, 30 for exercise, very specific to the lecture. And on Fridays will be a little bit of a review. Like I may just pick any topic from the previous 3 lectures. So this one, it shows how it is. See, I got already, I can see, if I go back and see what I see, I'll show you what I see. Let me do this then. So I'll share myself screen, start broadcast. Now you should see. No, start broadcast. So you have to stop sharing, Nikolai. Okay, now I think I can share screen. Okay, start. Okay, I think you can see. All right, that's what I see. Oh, what happened? Screen. Okay, now you see what I see. I see that 5 out of that 6 people have already responded. 5 out of 6 people have responded well. And that is what I see in terms of responses. I see in real time what you're doing. Now it says 5 minutes. I don't know how that works. So if I do edit, okay, I cannot do edit, cancel. So I think from the time you start, you get on it and you start it, you have 5 minutes to finish it, each one of you. But in any case, try that, practice a little bit with this, and you are going to remember something too. It's a useful thing, to try it a little bit as an exercise. Okay? Now, with this, any questions you have for me? This Sunday, I'm going to give you a simple homework. So we start warming up on things that you have already seen in the past. And this homework is going to give you an opportunity to do also a review. Now, before you guys try to, I see 7 out of 14. So the more they try, so that means that we need a little bit of practice in vectors. But that's okay. This is why I'm doing this. I'm taking this, I'm doing this test primarily to see who knows what and what I need to emphasize. Make sure that nobody is left behind in this class. Okay? Any questions you have for me?
I had a question on the Zoom. I saw that you posted the recording, but we need a password for it. So do you know what the password is?
You need, okay, now the recording, what I'm gonna do, you're gonna see how I'm gonna do the recordings like by tomorrow morning. Would that be okay?
Yeah, that's fine.
Yeah, by tomorrow morning, I'll put all of the recordings because I don't do, I found a different way of doing it, which you don't need passwords and stuff.
All right, thank you.
So sure, I'll put the previous one and today's.
When will we find out the correct answers to this?
I will publish the answers myself. And in fact, I will also keep them as a review. So I would like I can assign it as a review. If you see, you don't see it here. I can do unassign and then assign them as a review. And then you see what the correct answers are. And I can even put notes underneath it. But if there is a solution, then usually I will put the top hat answer underneath the top hat question. You're going to click and then you will see a document. You see, for example, let me go from here. Let's see. You see where it says example, top hat, quiz. When it's going to be highlighted, then the solution is going to be in there. Or underneath it, if I cannot highlight it, because also it has this one. Haven't I done it here? No, it does not have a link. But I will create a link and that's going to be the solution. Okay? Any other questions? The one last thing that I wanted to ask you is that, do you like, I was thinking about that it might be unfair to have Friday office hours so late in the day. Would you like me to move them on a Saturday or on a Sunday? Would it help you for me to have office hours instead of a Friday on a Saturday or a Sunday?
Sunday sounds good.
Sunday?
I don't know about anybody else, but yeah.
Sunday. But the weekend, you prefer the weekend instead of Friday?
Yeah.
Okay, what if I really do like Sunday, but earlier in the morning in case you have questions about the homework?
Yeah, Sunday in the morning sounds good.
Perfect. Okay.
I had a question in case we miss like this morning lecture. I know there's another that you teach another section of
Oh
this
yeah,
class.
you can connect to that one.
About.
In this case, I will need to make it available.
Yeah.
What I will do is always the same link,
Mhm.
and I will put it, I will send you an announcement today with the link for the other class, and I will do the same thing for them because I'm teaching the same things, all right? You're not, I mean, of
Right.
course, there are different classes that may have other questions, but they will be the same material.
Right. Yeah, I mean, just I want to be able
Yeah,
to
no,
get
that's a
prepared,
great
like you said,
idea. Yeah,
go to
yeah.
sleep. Yeah.
Mhm. That's a great idea. Okay.
Okay, cool.
All right. Very good. So I will see you on Monday. And I see mid-morning. Yeah, I'm not going to be very early on Sunday. That's not going to happen. I'm a night person too. I work very late at night, so I'm not a morning. I prefer if I can sleep late. Okay. Take care. Thank you. We'll see you
Thank
later.
you.
Bye.
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 Bye.